Hi everyone, and welcome to our lab script for this week in Psych 301, where we're going to be talking about correlation and regression. If you haven't seen them already, you could find my reviews for these concepts posted, where I have a Khan Academy style review for correlation and another Khan Academy style review for regression. I also would suggest you watch Dr. Siegel's recorded lecture from last week, which covers both of these topics in good detail as well. So, without further delay, let's jump right in. Today, I'm going to be doing this a little bit different than I did last time. I'm going to be using my key to walk through this, just because I don't have access to a second monitor at this point. And that second monitor kind of let me look at my key and then bounce back to the regular lab script while recording my screen like this. So bear with me. Of course, the key and the lab script are both posted, so you can fill in and pause to fill stuff in as you go along if you're trying to follow along like we would in a regular tutorial. But let's dive right in. So first, I'm going to run my knitter chunk as usual. I'm going to load my packages here, which is just tidyverse. This option SciPen equals 999. This just tells R to turn off scientific notation. Excuse my cursor there. To turn off scientific notation. Dr. Siegel tends to leave it on. I just prefer to have it off. And I'm going to go ahead and read in my data, which is this marketing.csv data set that is also posted for this week. Now, if I read this in, it's a data set that is comprised of 150 observations, and we'll just take a quick look at it. So here I have 4 continuous variables. I have YouTube, Facebook, newspaper, and sales. And as the little background prompt in the coding file suggests, the script file, is that this data set contains the impact of 3 advertising medias, that is YouTube, Facebook, and newspaper, on the sales for 150 unique products. So each row or each quote-unquote participant is a product. And for each of these products, the marketing team decided to spend X amount of dollars on YouTube advertisements, X amount of dollars on Facebook advertisements, and X amount of dollars on newspaper advertisements. And then they also collected the overall gross sales they got for that particular product. And then the last little note is that these are recorded in thousands of dollars. So where we see 27.6, that's really $27,600 and so on. And so we have a few goals. In the first part where we talk about correlation, our goal is going to be to do a correlation analysis with these data. So we want to A, calculate the correlation, B, see if that calculation is significant, or see if, that correlation is significant. And we're testing against the null hypothesis that the population parameter, which is this Greek row here, this kind of like fancy P, is 0. Where 0, if you remember, means that 2 variables are not statistically related or that they are not correlated. So we're basically testing the null hypothesis of, is this correlation, are these variables correlated? And are they correlated in a way that's significantly different than if they were not? So we'll go through that. I'll also show you how to produce a graph, a visualization of our statistical relationship or of our correlation, and in fact of our regression for that matter. That would be a simple scatter plot with a regression line. And finally, we'll demo a correlation matrix that contains multiple variables. So basically, each variable can be correlated with every other variable in the same way that we just correlate 2 variables normally. And we can look at the whole data set as a matrix together and also look at all of the significance tests for that data set as a matrix together, which is a lot more common in practice. So I'll show you a way to do that as well. So let's go ahead and dive right in, and then we'll also come to part 2 for regression analysis, where I have a couple other things I'll show you. So the first part of this lab script was to use the appropriate function to obtain the correlation coefficient for sales and YouTube. Here, the appropriate function would be this core function, or COR. And the way this function works is we're going to put in 2 vectors or 2 variables. So I have dat YouTube and dat sales. And what this is going to do behind the scenes is everything we saw in our Khan Academy review or in lecture. where we calculate a covariance, we calculate our product of the standard deviations of each variables, standardize that covariance by dividing by that product of standard deviations, and ultimately getting that standardized correlation coefficient, or that PPMC number. So if we go ahead and run this, we'll find that if we look at YouTube and sales, those two variables, there's a really, really high correlation here, 0.832 or thereabouts. Remember, our maximum correlation for a positive correlation is a positive 1. So this is very, very strongly related. These variables are very strongly related. So as YouTube spending goes up, so too does gross sales in a very strong way. Those two variables are very related. They covary quite strongly together in a positive direction. Next, we have this code chunk here, which is copied out of the lecture slides and is a code chunk that is creating a function called critical R. Now, this critical R function that Dr. Siegel wrote in his lecture is a way of calculating a critical value, or I should say obtaining a critical value for our R statistic, or for our correlation coefficient. The way we do this is that our correlation coefficient can actually be transformed into a t statistic. So even though we have like a separate R table in our textbooks and things, it's really a t distribution that's been transformed kind of behind the scenes. And so we make use of that stuff within this function. So what we're doing is we're naming the function critical R, as you see here. We're saying that this function is going to take two arguments. It's going to take n, which we're taking to represent sample size, and it's going to take alpha, which we're taking to represent the type 1 error rate we want to set for our hypothesis test. And we have this to default be just 0.05. So if we don't specify anything in particular for alpha, it'll default to alpha equals 0.05. And here's what's happening within this function. We're going to enter it's going to calculate a degree of freedom term first, and it's going to use that using whatever sample size we enter into the function. And it'll take that -2. So that gives us our degrees of freedom. Next, it'll calculate the critical value on a t distribution, and it'll use that using that qt function. And because we want to make this a two-tailed test, it's going to take alpha divided by 2. And it's going to use that degree of freedom term that it calculated in the last step here to specify on that t table that's going on in the background of all of this, which t value to look up. So here it's saying, okay, this is the area under the curve we want to look up. Here it would be 0.025. So give me a 0.025 slice, or a 2.5% slice with this degrees of freedom. So that specifies which t distribution it's going to find that 2.5% slice for. And then lower tail equals false just tells me to give it the positive value for that critical t. Remember, on a two-tailed test, our critical values are both negative and positive. For example, a two-tailed z-test, it's negative 1.96 and positive 1.96. So this is just telling me to give me the upper tail, or the positive version of whatever our t critical value might be, given whatever our degrees of freedom are. So in other words, to put that in a short sentence, this critical t line here is using the degrees of freedom we calculated. That's using the sample size we put into our function, and it's generating a critical t value that would be used on a t-test. What we're doing in this next step is we're using that critical t value that we just calculated in an equation to calculate a critical r value. A way you can think about this is that we're simply transforming that critical value for t into a critical value for r. And finally, this function will return that critical value for r. So it'll return whatever it calculates in this line here. I've put some notes in here. If you hover your cursor over these, you can kind of see what's going on. The equation needed to transform t n minus 2 degrees of freedom into our r critical value is this right here. So this is what's happening on that last line of that function. We're taking the t-value squared, dividing it by the t-value squared plus the degrees of freedom, taking the square root of all of that, and then we get our R critical value, whatever that is. So really, when we actually get this function ran here, and this is now a custom function for us to use, you can see it in your environment. Again, it takes those two arguments. I can start to use it. And because we set alpha to be 0.05 by default, unless I really feel strongly that I need to change that, I can just leave it out of the function altogether. So in this next code chunk here, I've got my critical value of for a sample size of 150. And if I run that, I see that I get 0.16. So if I have a correlation whose absolute value is greater than 0.16, then yeah, that's going to be a significant correlation. So here we have a correlation of 0.832 or thereabouts. That is definitely larger than 0.16, so the correlation here is significant. One way that you could also code this out is notice that I have this abs here. That's short for absolute value. Then I enter the correlation here and say, is the absolute value of my correlation greater than that critical value when there's 150 people, or in this case, products? And it'll spit out a logical, which is true. So true, I should reject the null hypothesis. The reason that we put this in absolute value here is because this critical R, we told it to take it from the upper tail, which gives me the positive value. But because this is for a two-tailed test, you could have you could reject the null hypothesis as either being more negative than the negative critical value or more positive than the positive critical value. In other words, extremity can go in both directions, hence it's a two-tailed test. So if this correlation happened to be negative, that's why I'm putting this within an absolute value function ABS here. So it would take that negative and just make it a positive so that this true would still apply to a negative correlation that was lower than the negative critical value in a two-tailed test. So there's that. Now that's great and all, and this is a really fun activity. Well, I say fun. It's fun for me. I'm not sure how fun it is for all of you, but it's a really useful activity in showing us how to create custom functions. But as you can imagine, this has already been done for us in the context of a correlation. And that's what this core.test function does, similar to like a t.test function. Here, we're just going to do the same thing. We're going to put our two variables here. So dat $sales, correlate that with dat $YouTube. And it gives me some really nice output that includes some more information that I did not have once I did my critical R function and everything else. So I could actually see this is my t value before it gets converted. I can see that that p value is really small because I turned off scientific notation. I can see it's just painfully small. So we definitely rejected the null hypothesis that our correlation was equal to 0. And it even gives me like a confidence interval around my correlation of 0.832. Also just gives me the correlation estimate in and of itself. So if you're doing this, my money is for you to just use core.test rather than trying to create your own custom function. Although this is pretty cool, and it does give us an opportunity to also talk about how we transform R to T or T to R and all that to actually run that hypothesis test. Next, we wanted you to create an appropriate visualization to show the relationship between sales and YouTube. And truth be told, you could do so with something as simple, this should be DAT, not DAT2, just DAT, excuse me. You can do something as simple as just creating a scatter plot with this. So I'm going to delete this plus here real quick and just run this line. This is enough to show that relationship. This is a scatter plot similar to things you saw in lecture and in my review as well. I've added a lot of stuff here in this key. For example, I've added geom smooth, and this just creates a line. Notice that if I get rid of this method argument here, it creates a curved line to fit this, and I'll actually run it as scatter plot. It kind of creates this nice curvy line that follows the data. However, To my eye, this data looks linear enough for me to feel comfortable using a linear regression. So I'm going to put method in quotes LM for linear model, which is linear regression, and it'll fit a straight line to that data for me. So that is my linear regression line. And I feel comfortable doing that because I can look at this relationship and feel pretty confident that this is of linear form. So if we look at kind of like the shape of this data cloud in general, I can see that it follows a pretty clear trajectory, that there's no major like curves or S shapes or bends in this data. So it looks like it's a linear form to me, which means using things like a Pearson product moment correlation to assess the strength of this correlation is appropriate, as well as using something like a linear regression to do some prediction about this. It also seems appropriate. So I've got this graphing object here that I saved as Scatterplot, and I'm calling here as the object Scatterplot because I'm going to reference this again with the linear regression in just a couple of minutes. So I'll just run that whole chunk, and that's what it should come out nice and clean. And again, these are in thousands of dollars here. So we can see that as YouTube spending increases, as we go down this x-axis, gross sales increases, it goes up the y-axis. So this is a positive correlation here and a pretty strong relationship to boot. One thing I'll quickly say is if you look at the dots and how they cluster around the regression line, the more tightly clustered those dots are around that line, the stronger the correlation. The more spread out they are, the weaker the correlation. So moving on, you can use this same function core to generate an actual matrix of correlations among numerous variables. So basically, if I want to know the Pearson's R between every single pair of variables, I can do so by just entering the data set into core itself. Now you need to be careful because this will give you correlations for every single variable that's in this data set. It just so happens that the data that I've given you here has 4 variables that are all continuous. And it doesn't have anything else, like it doesn't have participant ID numbers, it doesn't have like grouping variables or anything like that. So I'm comfortable just putting the whole data set in here. If I wanted to put a subset, then I could always put some reference brackets here and tell it to give me columns 1 to 10 or 1, 2, 7, 8, 14 or whatever I'm interested in looking at. But for here I can just put in dat. So if I run that, I get my correlation matrix. And you notice that this is symmetrical across the diagonal, so it kind of just repeats itself. So the correlation between Facebook and YouTube is right here, but it's also right here. So you can kind of look at the lower triangle is how I tend to focus on it, just this group here. And I can see a few things that for certain product marketing strategies, Facebook and YouTube have a pretty low correlation. It seems like people are probably more apt to choose one or the other, though they do change in a positive direction together. Between YouTube and newspapers, that's actually negative. So the more people tend to spend on YouTube advertising, the less they tend to spend on newspaper advertising. Although that correlation is so low, they might as well be uncorrelated. It's so close to zero. Kind of the same for Facebook for that matter. It's pretty close to zero, the correlation between Facebook and YouTube. And then as we saw, the correlation between YouTube and sales is quite large. I could also just look at the sales row and see that the correlation between YouTube spending and sales is large. The correlation between Facebook ad spending and sales is also fairly large, I'd say moderate. And the spending between newspaper advertising and sales is still positively correlated, but not as positively correlated as YouTube or Facebook ads. In fact, if I go back and again look at my critical R, that was 0.16. If I scroll down here and I see that I have a correlation of 0.145 or 146 for newspaper and sales, that's likely to be an insignificant correlation. It would not reject that null hypothesis that the population correlation is equal to 0. So here's my correlation matrix among all the variables. I can see how what I would consider the predictor variables or the independent variables, how they correlate with one another. And then I can also see how each of those predictor variables independently correlates with what I'd consider the dependent or the response variable sales. So that's one way to do that. I also have included some code here to do the hypothesis tests together. So what I just showed you was just the correlation coefficients, but not their corresponding hypothesis tests. This uses what's called the HMISC package. H is just the letter of someone's last name, MISC for miscellaneous, so it's just a package of miscellaneous functions by this person. You can install this if you don't have it by uncommenting this line, running that code, and then recommenting it out. And then this is just going to give me two things. It's going to give me one, a correlation matrix, although sadly it's kind of abbreviated by only 2 decimals. It only rounds to 2 decimals. But then it's going to give me another matrix, and it's going to give me another matrix of p-values. So I can see the p-value for Facebook and YouTube is insignificant. The p-value for YouTube and newspaper is insignificant, so YouTube is not significantly correlated with either of those things. However, YouTube ad spending is significantly correlated with sales. Facebook ad spending is significantly correlated with sales. And newspaper ad spending is unfortunately not correlated with gross sales. So this would fail to reject that null hypothesis. We could say that statistically speaking, newspaper ad spending and increases in sales are not related. So there's a whole bunch of hypothesis tests all done together. And I'm sure there's other ways to do this. I know there's something in the PSYC package as well. But this is the most straightforward one, in my opinion, at least at this stage in your educations about this stuff. There's also really cool visualizations that you could do, but I'll leave it to you to explore those on your own if you have any interest. So the next question here is, I asked a bonus question, at least this is what I would usually do in lab and I've done a few times, and that's if you can figure out how to calculate a p-value for a correlation without using core test. And this is kind of a cool practice. I like to think about this in terms of doing it as a function and writing my own function rather than doing this in some sort of core test type of way, or doing it in just like some sort of calculator type of way. If you're going to calculate it out, you might as well make it versatile so you can use it over and over again. So here, I've got a function called r.pval, which is going to take whatever your correlation is and your sample size. And when you enter those two things into your function, it's going to use those two pieces of information to calculate what your p-value should be. So this is actually almost identical to the critical R function up here. You'll notice one little thing. When we calculate a critical T, we use this QT over here. And that gives us the value that kind of demarcates some slice of our distribution. So it gives us the critical value that defines like that 2.5% slice that we'd call a rejection region. Here, we still do all of this stuff, but when we get to our T, we use PT instead of QT. And if you recall from way back when, or maybe you just put this on your assignment, PT gives us the probability space, or it gives us the area under the curve, not the value on the x-axis that slices up the distribution, but it gives us the actual proportion of area under the curve of the slice that we make. So what we're doing here is we're saying here's our degrees of freedom that we used using our sample size, or that we calculated using our sample size. Here is our absolute value of R. So if we have a negative correlation, that works fine too, but we're just going to make it absolute to make our function a little bit easier. We're going to take that R and transform it into a T value, and then we're just going to look up the probability or the proportion of area under the curve associated with that T value towards the positive tail, and that makes sense because we made this an absolute value as well. So instead of calculating like a critical T, we're actually calculating R obtained, T obtained, and the p-value associated with that t obtained. And that when we run this, it returns that actual p-value. So here, this is the correlation between YouTube sales or ad spending and sales. And I have 150 people. So if I run this for the positive direction, it gives me my p-value. I just added a negative here to show you that if I run it for a negative correlation, it also gives me my p-value. And perhaps a little bit more accurately, instead of entering the correlation by hand here, I can just put the correlation function in that spot, which will calculate the actual correlation without any rounding or anything like that. So if I run this whole thing together, you'll see that all three of these instances work. The first two are identical. The third one's a little bit different, but that's because this core function just did a little bit of, it didn't round as much for me, and it gave me kind of a little bit more accurate or precise estimation of that correlation. So the p-value is just a little bit more precise in that way too. So that's the gist of our code for correlations, and to be frank with you, we did some cool stuff with this r.pval and this critical r functions. But if you eliminate those things as being a little bit superfluous or kind of just a little bit of extra stuff, really doing a correlation analysis in R, the only functions you really need to know to get at least have a bare bones way of doing it is core test, if you want to get the hypothesis test done for you, and maybe this R core, which is in that HMIS package if you want to do multiple correlation tests at one time. And then of course plotting is also just a nice touch as well. So that's part one, and that's correlation analysis in R. Now let's look at regression analysis here in part two. So I'm going to show you a simple regression, and when we say simple, we just mean that there's one predictor variable and one response variable. Or one independent variable and one dependent variable, if you like that language better. And when we start to say multiple regression, that's a reference to there being more than one predictor variables or more than one IVs predicting only one response or dependent variable. So let's jump into this then. So here I'm saving as an object name reg, this function, or the output of this function, which is LM for linear model, sales, that's my dependent or response variable. This is that tilde, so the same thing we saw in like the t-test function syntax. YouTube, which is my independent or predictor variable. And then I'm just specifying where the data is coming from, and it's coming from my dat object over here. Like any statistical output or statistical test, like a t-test function we ran, if I run this, it's going to save as this list object. And it's going to have all these different things. It has my coefficients, my residuals. Residuals are the errors associated with our prediction for every person, and so on. But I could also use this summary function with that object to get a nice kind of organized and compiled set of results. So if I run summary reg, I get this nice output here, and this tells me a few things. First, it tells me about my residuals. Now, if you recall from the lecture or from my review, a residual is the distance between what the model predicts for somebody and what they actually got. So our model predicts things using a regression line. This line here is everyone's predicted, or every product's predicted gross sales given their amount of YouTube ad spending. So I can see that prediction line here. And then each product has its actual amount of gross sales. So for instance, whatever this product is here, its actual sales are there, its predicted sales are here, and that distance between the line and that actual dot, that is the residual, or that's the amount of error in the prediction. And when you kind of conceptualize that as it's being a distance between the line and the actual dot, you might get a better idea of why when dots are closely wrapped around that line, when they bunch up around that line pretty tightly, that's a strong correlation because there's less error. If we had a lot of dots that are kind of really spread out about the line, well, that suggests a weaker correlation because there's more error there. So here, that's just some information about those residuals. Uh, we generally don't need to interpret that too much. What we're really after, first of all, is to know whether our regression model itself is significant. So we need to look at model fit statistics and effect sizes as well. We should probably do that first. Now, when I say model fit, that's a reference to how well the model fits the data. And I know that using this term model is a little bit new in this course and in your statistical training so far. What we mean by model is I made this model that says sales should be predicted by YouTube spending. I could have made that any way. Maybe I could have said sales by Facebook spending or sales by YouTube and Facebook spending. I basically get to build this idea or this conceptualization into this statistical model. And we can build all sorts of different models, and all sorts of models can fit the data and fit them well. So we want to make sure our models are backed by some sort of theory if we're doing some serious science. Here, I want to first make sure that this model at least fits the data well. If the model isn't a good representation of the data in general, then we don't need to go on interpreting anything specific about it. So we do that using an F-test, which gives me a ratio of how well my model predicted things against how much error in the prediction there was. And it turns out in our case that we got a really high F statistic and a really low p-value associated with that. So this tells me that my model was very significant. It's very high ratio in terms of there being good prediction variance to error variance. There's a lot more good prediction variance than there is error variance. And this is also reflected in this R squared here. It's labeled multiple R squared because we can have multiple predictors, but when we just have one, it's just R squared. And here it's 0.6917. If you remember, the interpretation for our multiple R squared, or R squared's effect size, is that it gives you the proportion of variance in the dependent variable that is explained or accounted for by the variance in the independent or predictor variable. So here, YouTube sales, or excuse me, YouTube ad spending explains almost 70% of the variability in gross sales. That is, changes in how much people spend on YouTube ads expresses itself in about 70% of the changes in how much gross sales there are. And that was actually a pretty crude way to say that, so be careful if you say it like that, but the correct way would be to say that 69% of the variability in sales is accounted for by the variability in YouTube ad spending. Okay, so that gives us a good starting point. We know that the overall model is significant. It fits the data well. And now I can go towards looking at this table of coefficients here. And when we have a simple regression with only one predictor, there's two coefficients that we get, and there are corresponding hypothesis tests for significance, which are done as t-tests here. We have the intercept term. This is that beta subscript 0 parameter that we saw in the reviews. And this intercept term tells me how much of the dependent variable I would have if my independent variable was 0. And that makes sense because that's where our axes cross, right? So let me go ahead and run this whole thing so we get a scatter plot too. This tells me that my intercept is about 17.76. So when I have 0 YouTube ad spending, that would cross this y-axis at about 18, and I can kind of see that here. If I were to keep going with this line, right about there is 18, or 17.76. So that's my y-intercept. The significance doesn't really mean too much when we're just doing a simple regression and with continuous variables, so I don't need to really think about that as much. And then here is my estimate for my slope. So this tells me that for every 1 unit increase I have in sales, I have a 0.57 unit increase in YouTube, or that, my rise over run is 0.57. So if I look at that scatter plot again, it's hard to visualize here because I don't have tick marks based off of 1. But basically, every time I go over to the right, 0.6, I'm going to go up 1 unit in gross sales here. So I don't know, this is about 21. If I go up 0.6, then I'm at 22, and so on, 23 going forward. The way to interpret that would actually be something like this. And remember, these variables are in the thousands of dollars, so I'll interpret it as such. For every $571 that I spend on YouTube spending, my gross sales increase by $1,000. So that's what we mean. For every 0.57 unit increase in YouTube, we get a 1 unit increase in gross sales. So that's pretty cool, and that's a really good prediction device for us when we talk about a regression model as prediction. We can predict how useful that strategy would be of investing in advertising sales dollars. You can think of this as something like a college admissions thing as well. The college admission boards collect a lot of information from you, like your GPA, your if you're in the States at least, your ACT or your SAT scores, and all these things. And they probably run some regressions like this to figure out which of those variables is the best predictor of how well students tend to succeed in their programs. So that scenario that I just posed to you is actually an example of a multiple regression because it included multiple independent variables like GPA and test scores and the like. So let me go ahead and show you that as well. And I'll do this to close out our session here. Here I have a multiple regression. I'm going to save this multi-reg named object, and I'm going to save the results of my linear model or my regression here again. The only difference between this and what I did last time is I've said plus Facebook and plus newspaper. So the syntax here is slightly different than what we saw when we did ANOVA and we used the multiplication asterisks instead of the pluses. And so I'm going to run this, and I'll run the same summary, and this is what I get. First, I'll look at my model. I can see that my model is still significant, and that by adding Facebook and newspaper, I went from about 0.69 to 0.86 in terms of my multiple R squared. So I can interpret this as saying that about 86, almost 86.5% of the variability in gross sales can be explained or accounted for by the variability in the YouTube, Facebook, and newspaper predictors, variables, all those three things together. So once I know that this model is significant for my F-test, and then it explains a meaningful amount of variability looking at the R squared, I can look at the actual coefficients themselves. The only difference between this test and the one I just saw is because I added 2 variables, I now have 2 more regression coefficients to interpret. And these again are going to be slope terms or slope parameters. It's kind of hard to describe this without a visualization because as we add more variables, we add more dimensions. So this would be like a 4-dimensional plot, which I can't really show you at all. But the idea here is each of these gives me an idea of how sales change with these included in the model. So you'll notice the YouTube parameter changed a little bit from what it was. It went down slightly because we added the Facebook and newspaper parameters. So when I have all 3 of these predictors in the model, for every $554 spent on YouTube spending for a product, the gross sales increases by $1,000. For every for every $554 I spend and $160 I spend on Facebook, and basically nothing I spend on newspaper, my gross sales increases by $1,000. So I can see here the significance tests here. I can see that my YouTube and my Facebook predictors are significant, but my newspaper predictor is very much not significant. So, newspaper spending for advertisements does not really predict gross sales very well in the slightest. So, in that regard, it's more a better strategy for me as a marketing firm to invest in YouTube and Facebook advertising than it is for newspaper advertising in terms of increasing my gross sales. So that's the very short gist of how to do correlation analyses and regression analyses in R. And I'll also note we did kind of skip over a lot of things, like we didn't talk about assumption checking or anything like that. You'll get a much more in-depth and deeper understanding of regression analysis in particular, and correlations too, if you take Psych 411 or Psych 911 if you're a graduate student. That's a class taught by Rochelle Filati that is meant to follow the ANOVA class that is 410 taught by Dr. Mike Moran. If you're interested in learning a lot more about quantitative statistics and how they're used in psychology and growing your quant skills to something that is really insightful and valuable, I'd strongly suggest you check out those two classes going into your senior years, or if you're doing an honors thesis, those are great classes to take as well. But for now, that's all I've got relative to our lab script this week. As always, I'm wishing you all the best of health and peace of mind during this whole pandemic. And like I keep saying, please be mindful of your mental health as well. Do what you can to keep a level head on your shoulders as social isolation and distancing kind of bears down on all of us. So until I talk to you or see you next time, have a good week. Keep up with your studies and yeah, be well. All right. Bye.